All right, so this is chapter 11, section 9, called binomial distributions. We've seen the word binomial before. It is a polynomial with two terms, and usually we raise it to a certain power. We did the little Pascal's triangle with this last time we saw it. Our learning objective is to find binomial probabilities and to use binomial distributions. We were using Pascal's triangle to multiply out binomials, and now we're going to use it in application with probabilities. So we can use binomial probabilities in situations involving two possible outcomes. But first, we need to be able to identify which experiments we can use these for. So a binomial experiment has the important features. There are a fixed number of trials. Each trial has two possible outcomes. The trials are independent of each other, and the probability of each outcome is constant throughout the trials. Easy peasy, lemon squeezes. So you guys, on these notes, make sure you're highlighting what I'm highlighting and you're writing down what I'm writing down. That way you can get full credit. All right, so in 11-4, we saw this tree diagram to find probabilities, and actually that was a part of the learning objective, is to use tree diagrams to find the probabilities. So we copied this one about the basketball player shooting free throws. In fact, two of them. So we have two branches to our trees. So we've got, if we start at the beginning of our tree, her probability of making a free throw is 90%. So when we go along this branch of making it, that's where the 0.9 comes from. Then you have to do the converse. The possibility that she's not going to make it is 1 minus 0.9 or 0.1. Then she's either makes it or misses it. Then the next time she's back at it, at the free throw line, ready to shoot the hoop. And again, the probability resets. She can either has a 0.9 chance of making it or a 0.1 chance of missing it. So when we calculate the probabilities, so if you look, the probability H is for hit, so she's going to hit it. The probability that she hits it twice is 0.9 squared. So you just go along this branch, 0.9 times 0.9, which is 0.81. So that's how we use the tree diagram to find probabilities. Now, the probability that she's going to make it and then miss it, or miss it then make it, is the probability of one make, which is 2 times 0.9 times 0.1. You multiply those together, you get 0.18. So the probability that she's going to hit it and make it, or make it and hit it, order doesn't matter on this, is 0.18. Where does the 2 come from? All right, so this 2 comes from the fact that there are 2 branches where she misses it and makes it. And then lastly, what is the probability that she's going to miss it and miss it? So you take that 0.1, it's only one branch, and you take that 0.1 and square it, and it is, she's got a 0.01 or 1% chance. All right, so now we're going to start combining these out. Check out this scenario here. Suppose the player needs to make one of two free throws to win a game. The purple on the red table shows the probability of 2 hits plus the probability of 1 hit is this 0.81 plus 0.18 is 0.99. That's a 99% chance. So the basketball player shoots 2 free throws, each independent of each other. So it counts. We can use this scenario. the player will succeed on 0, 1, or 2 of them. So she'll either make none of them, make one of them, or make 2 of them. These are the only possible outcomes. All right, so let's flip the page and get this binomial probability formula. I don't like the way this is written because if you look at, to me, I want to be able to use formulas fast and quick. So go ahead and highlight the probability formula. But look at all the letters running around in here. We've got a P, an X, an N, a C, a little p, same x, a q, same little n and same little x. I want to know what each of these guys is, so we're going to write that right next to this formula. So what does big P stand for? This one right here. Yeah, sounds for probability. All right, so what about x? The successes. N. Yeah, it's the number of trials. And then we have, what is the C? We did this in section 1. So this is combination. So it's N choose X. All right, what does little p stand for? Little p is the probability of success. Q is the probability of failure. Now, the probability of success plus the probability of failure should always equal 1. All right, I think that identifies everything in this crazy formula. One little tiny formula has all this business going on in it. So let's see how we break down a problem and use its components in this formula. As a part of a promotion, a store is giving away scratch-off cards. Each card has a 40% chance of awarding a prize. And let's highlight information as we see it. Definitely know that 40% chance of awarding a prize is going to be important. This 5 cards is going to be important. Find the probability that exactly 4 of the 5 cards will reveal a prize. So what do we know? We know the number of trials, we know the number of successes, and we know the probability of success P. We need to know the probability of failure and the probability of picking exactly 4 winning cards. So we need to figure out, can we use binomial probability? We need to get the probability of our failure, and we need to use the binomial probability formula. All right, so determine if it's a binomial experiment. The situation involves 5 repeated trials, so it's a set trial. Each trial has 2 possible outcomes, win or not win. Probability of success is a constant. It's 0.4 throughout the trials. Where did this come from? Did they just Where did the 0.4 come from? It was given to us. The trials are independent. The outcome of scratching one card does not affect the probability of any of the other cards revealing a prize. All right, so we know that the number of trials is 5. We want to be successful 4 of those times. Probability of success is 0.4. The probability of being unsuccessful is 1 minus 0.4, which is 0.6. So when we take a look at our formula, we're going to plug all these numbers in. Probability of 4 is 5 choose 4 times 0.4 to the 4th times 0.6 to the 1. Because, and just to identify, n was 5 minus x is 4. That's where that 1 comes from. That was nothing. Not always going to be 1. So when I'm not near my graphing calculator, I can, to go 5 choose 4, you can definitely go combination calculator. And I've already used it. And we're going to be 5 choose 4. And you go calculate, and it's 5. So that's as difficult as that gets. That's where that 5 comes from. And then it's just a number crunch. 5 times 0.4 to the 4th times 0.6 is 0.08. So the probability is about 0.08 that exactly 4 of the 5 cards will reveal a prize. So let's do a couple of these problems. So the difference, what they're asking here is they want you to change your x value from 4 to these different numbers. So let's do 2 and 3. So what if we change it from 4 to 2 and 3? How does that change our equation? So let's go probability of, so we'll do 2 first. 2 successful cards. We still have 5, but now we're going to choose 2. We still have a 40% chance of winning, but instead of 4, we're going to be 2. And it's still a 60% chance of not winning, but instead of 1, it's going to be 5 minus 2, or 3. Let's do probability of 5. 5 minus 5 is 0. Alright, so let's take a moment, shove this into our calculator, and come out with our results. Alright, so when you do the math, you get 5 choose 2 is 10, times 0.4 squared times 0.6 cubed is 0.3456. Then probability of getting 5 is 5 choose 5, which is 1, times 0.4 to the 5th, times 0.6 to the 0, which is 1, and you get 0.01024. All right, now we're going to see, we're going to take the binomial theorem, and we're going to do a little review on, this is a little bit new because we're using combinations instead of Pascal's triangle. Pascal's triangle, the numbers we get from there can be explained or defined using combinations. So for every positive integer n, a plus b to the n power is n choose 0 times a to the n plus n choose 1 times a to the n minus 1b plus n choose 2 times a to the n minus 2b squared, and all the way. So what I like, the way I remember this is my a whatever guy's in front, he starts at the n power, and my b is nothing, and then my b increases 1 power at a time, and my a decreases 1 power at a time. So whoever's first is increasing in power, or whoever's first is decreasing in power, and whoever's second is increasing in power, until at the very end, the power switch happens and A completely goes away and B is left. So I want to show you how this works. If you look at problem A, we start out with x plus y to the 5th. So for A, we're going to use x, and for B, we're going to use y. And we're definitely going to the 5th power. That's our n value. So then you write it all out. 5 choose 0, x to the 5th. Remember, our first value starts in the biggest power. And then you go 5 choose 1, x to the 4th, so it decreases by 1, and then y appears. 5 choose 2, x to the 3rd, y squared, plus 5 choose 3. When you simplify this out, 5 choose 0 is 1 times x to the 5th. 5 choose 1 is 5 times x to the 4th y. 5 choose 2 is 10. We did that together. 5 choose 3 is also 10. And then 5 choose 4 is 5, and 5 choose 5 is 1. We may get problems like in B that have coefficients. And in that case, we have to multiply. We do the same process, but we are multiplying the coefficients, where we apply the power to the coefficient and then we multiply it through. So when it says what is the third term of a binomial expansion, we really only have to, we don't have to do the whole thing like in A. We just grab, I know that there's 4 altogether, so I'm going to take and use the n choose n minus 1, a, b, n minus 1, and plug it on in. All right, so let's do that together in this got it. For A, we're going to use 3x, and for B, we're going to use y. So I'm going to go, our n is equal to 4. So I'm going to go 4, choose 0, 3x to the 4th, plus 4, choose 1, times 3x to the 3rd, b. Let's move this out of the way. I'm marching it. It's not b, sorry, it's y. Plus 4, choose 2, 3x to the squared power, y to the squared power. 4, choose 3, 3x to the 1 power, y to the 3rd. 4, choose 4, 3x to the 0, y to the 4th. All right, when you calculate all these combinations, you get 4 choose 0 is 1, times 3 to the 4th power is 81, times x to the 4th. 4 choose 1 is 4. 3 to the 3rd power is 27. X to the 3rd power is x to the 3rd, and y is y. 4 choose 2 is 6. 3 squared is 9. x squared is x squared, and y squared is y squared. 4 choose 3 is 4. 3 to the 1 power is 3. X to the 1 power is x, and y cubed is y cubed. 4 choose 4 is 1. So remember, just to do a little snippet, Pascal's triangle. If you're doing 4th power, it's 1, 4, 6, 4, 1, which matches our 1, 4, 6, 4. Remember when we did Pascal's triangle? That was so much fun. All those days ago. All right, now we're going to simplify this all down to one concise number. This is 81 x to the 4th. Whew. 27 times 4, well, 20 times 4 is 80, and 4 times 7 is 28. 80 plus 28 is 108. 6 times 9 is 54. 4 times 3 is 12. And that should be the answer. I, of course, have my little cheater. Make sure it matches. Yes. All right, so now we're going to put the two together, binomial theorem and binomial probabilities. To find the full probability distribution for a binomial experiment, we're going to expand the binomial p plus q to the n. For example, suppose you guess on 4 questions of a 5-choice multiple choice test. For 4 questions, n is equal to 4, that's our number of trials. Probability of guessing correctly is 1 out of 5, because there's 5, A through E. So the probability, 1 divided by 5 is 0.2, so the probability of success is 0.2, which means the probability of failure is, so you can 0.8. So we are going to use a binomial expansion. So taking the 1, I guess this look familiar, 4, 6, 4, 1. Do you remember that from, if there's 4 trials, it's 4 choose 0, 4 choose 2, or sorry, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So the probability that you're going to get 4 correct is 0.2 to the 4th power, because our p is 0.2. That matches this 0.2. Plus the probability you're going to get 3 correct is 4 times 0.2 to the 3rd times 0.8, because remember 0.8 is our q. And so on and so forth. Why they chose to display this on a graph right now isn't very helpful to me as I'm trying to plug the numbers in and get it. So the probability of getting 4 correct answers when you're guessing is a less than 1%. The probability of getting 3 answers correct when you're guessing is 2%. Probability of getting 2 answers correct when you're guessing is 15%. And the probability of getting 1 correct is about 41%. But look, the probability of getting 0 correct is also 40%. All right, so let's apply this to a problem here. Now, could you use Pascal's triangle if you don't feel like calculating the cubes? Oh yeah, yeah you can. So, and in fact, because I'm more comfortable with Pascal's triangle than I am plugging it in the calculator and figuring out, I'd probably use Pascal's. So let's look at this manufacturing problem. Each hour, a cell phone factory quality control tests the durability of 4 randomly selected phones. I don't think this 4 is going to be just a arbitrary number. If more than one fails, QC rejects the entire production for that hour. If in 1 hour, 95% of the phones are made, 95% of the phones made are acceptable, what is the probability that QC rejects that hour's phone production? So we're going to write a binomial expansion. Our number of trials is 4. Our probability of success is 0.05 because we are actually testing for rejection. So that we want to know what's the probability that the whole hour is going to get rejected. So the probability of rejection is 0.05. And the probability that we're not going to get rejected is 0.95. So if we use our expansion to expand this out, we get p to the 4th q0 plus 4 times p to the 3rd q1 plus 6 times p squared q squared plus 4 times p1 q3 plus p0 q to the 4th. So all we're going to do is plug those numbers in, chug it away on our calculator, and then add our probabilities together. 4, 3, or 2 phones fail. We have to exclude these values here. So let's write that down, excluded. Why are we excluding the 1 fail and the 0 fail probabilities? It's this one right here. We want to know if more than 1 fails. So that would be 2, 3, and 4. So we are not going to include the last 2. And I'll solve across this. There is a 1.4 chance that QC will reject the phones produced in the last hour. Let's see if we can repeat this. At the bottom. All right, multiple choice quiz has 5 questions. Each question has 4 answer choices. If you guess every answer, what is the probability of getting at least 3 correct? So let's set up this prop 5. In this case, we have 5 questions, so n is equal to 5. So the probability of guessing correctly, is that with your G? Is 1 out of 4. And then the probability of not getting it correct is 3 out of 4. So this is 0.25. This is 0.75. If you guess every answer, what is the probability of getting at least 3 correct? So this would be P plus Q to the 5th power. And so I'm going to use Pascal's triangle. Because I don't want to calculate all the combinations. So it's this one, the 1, 5, 10, 10, 5, 1. So it's going to be 5p4q plus 10p 3q squared plus 10p squared q plus 5 p 3q 4 plus q 5. So we line up our probabilities, the first one is the probability that all 5 will be correct. The second one is the probability that 4 will be correct. The third term is 3 correct. The next one is 2 correct. The next one is 1 correct. And the last one is 0 correct. We only care about the probability of getting at least 3 correct. So that is 5, 4, and 3 correct. So let's plug in the numbers. The probability of guessing correctly is 1/4 or 0.25. We got 5 times 0.25 to the 4th times 0.75 plus 10 times 0.25 cubed times 0.75 squared. And then we're going to chug those into our calculator. So when you do the calculations, you get 0.0625 plus 0.0146 plus 0.08789. You add all those together. All right, we had to make a calculation change. The probability 0.25 to the 5th power is 0.0000976. So with that modification, our outcome becomes 0.103, or about 10.4%.